Okay, so we're talking about a couple of different types of lines. That's how we're going to start. We have first constant lines, and for constant lines, we can say y is equal to 3. Okay, so when y is 3, y is always 3 here. It's never going to change. So if x, like we talked before, if x was 1, 2, 3, 4, 5, if x is 1, y is still going to be 3. If x was 2, y is still going to be 3. If x was 100, y will still be, 100, y will still be 3. So this graph looks like a line that's not changing. 1, 2, 3. And this is the graph of our line. One thing we realize if we're looking back at lines is that we talked a huge thing about change, about slope. And this graph, since it's not changing, has a slope of 0. It is not changing. Hence the definition of constant. So you can use regular words to talk about what's going on here. So how's your life going? Is it getting better? Is it getting worse? It's pretty much constant. It's not changing. Monday looks like Tuesday. Tuesday looks like Wednesday. Wednesday feels like Saturday. Nothing much is going on. Now, then we have the idea of things that change. So let's go ahead and move on with lines that change. And we're going to look at variables in lines. And that's going to mix it up. That's going to change our lives around. And our typical equation, like we learned in Algebra 1, is y is equal to mx plus b, where b we called the fancy word y-intercept, and m was our change, our slope. And slope could also be defined by rise over run. Whenever we have a change in math or science, it's always something over something because you're comparing what is the difference. Like if I'm driving my car and I'm driving miles per hour, well, that's miles over a change in time, hours, meters per second. So what happens is it's all about a change if I'm trying to measure a difference, or difference measures a change, okay? So we've seen this before. So if I give you y is equal to 3x plus 2, y is equal to 3x plus 2. Well, the change is 3 every time x changes. And I'll show that in a little bit. But the constant here is going to be 2. Regardless of anything, you're going to start off at 2. So let's set up a table, x's and y's. If we plug in x as 0, that's our starting position, I've already made $2. I'll rewrite that to make it look a little nicer. So it's 3 times 0 plus 2. I write the parentheses around the 0 just to make it clear to me I'm plugging it in, make it look nice. We can plug in 1. 3 times 1 is equal to 2. Nope, not equal, I'm sorry. Plus 2. 3 plus 2 is 5. Now let's plug in 2. 3 times 2 plus 2 is 6 plus 2 is, 6 plus 2 is 8. Now, we've done a bunch of tables like this, and you guys have seen it before. But again, I want to draw back to what is really going on here. Now, the slope we said was 3, and this could be rewritten as 3 over 1, which is rise over run. Please be aware that rise reflects an x change or a y change. When you use your hand, move your hand and move it up and down, isn't rise an x change or a y change? That's a y change, right? And that's really what we're referring to. This is a y change. And if I say run, that's an x change. So we can break this down in a more like comprehensible way where if x changes by 1, then y changes by 3. And let's see if that's true. In our example that we drew here, when x changed by 1, that was like a +1, then my y changed by +3, which is totally illustrated in our answers, in our numbers that we chose. If y changed by another one, if x changed by another one, then y changed by another set of 3, which is literally defined by our slope. Our slope says for every x change, we have a y change. And how much do we change by each? Okay, how much do we change by each? Okay. So one of the cool things is that now that you kind of get the idea of what slope and lines and how they're related, if I write 5x plus 4, okay, for my slope being 5 over 1, we can kind of predict without actually doing any math what's going to happen. If I told you, let's do our table again. If x is 0, x is 1, and x is 2. If I plug in 0, 5 times 0, well, that is 0. Come on, easy. So we're left with just a 4. But for every step after this, we can just follow our slope. If the rise over run, for every step I take, every 1x step I take, I have to take 5 y steps. So this is going to be automatically my next step of 1. That's going to be a change of 5. That's going to be 9. Next change, this will lead me to 14. You don't have to do the math anymore. Because the slope, it's very predictable. These are straight lines. Parabolas are not as predictable. But what happens is, as you guys get learning different levels of math and calculus, it turns out parabolas, x cubed, x to the 4th, they're actually all predictable. And they're all related, and we have ways of calculating them without actually crunching out every x value by plugging it in. It turns out computers don't think the way we do. Duh, right? So us as humans, we can actually see relationships. We can say, oh, know what? I can make that next prediction. But computers don't do that. Your computers will actually calculate plug in 0, plug in 1, plug in 2. They can't resist. That's how they're taught. So no matter how smart a computer is, we're smarter. This is what it is. They might be faster. Please understand, they might be faster in calculations, but we're still smarter. Till Arnold Schwarzenegger comes in breaking through my door and says, come with me if you want to live. Okay, so the idea of lines can be pretty easy. Now let's go ahead and talk about some fraction lines and some negatives at the same time. Negative 3 over 2x, let's do plus 1. So we have our y-intercept here is b is equal to 1, and our slope, m, is negative 3 over 2. Okay, that's our slope. Now we can plug this into a table. And when I'm plugging this into a table, I want to make sure you guys pick smart numbers. Pick smart numbers. Please pick smart numbers, please. So the first one we can always choose is 0. That's always an easy one. And for us, hopefully you've noticed this, or hopefully you know this already, but if I plug in 0 here, doesn't the whole problem cancel out in the front? And you're left with the y-intercept. So that's why we even call it the y-intercept, because that's what's always left when you plug in 0. When you look at the graph, the y-intercept refers to the line, so the y-axis here, and where does the graph touch the y-axis? Well, when x is 0, that's going to be 1 for this problem. That's always the easy point to graph. Start off with your y-intercept. We have to know where to start before we talk about a change. We can't talk about change if we don't know where you started. There's nothing to compare to. Okay, next step. If I go ahead and plug in 1, I do not want to plug in 1. The trick is, if you remember, to pick numbers that are divisible by that denominator. 1, I don't want a fraction. You guys want to do more fraction work? No, Algebra 2 is about being smarter, okay? Not working harder, Working hard is important, but we want to think smarter. So instead of writing 1 here, I'm going to write 2. Because when I plug in negative 3 over 2 times 2, guess what happens to those 2's? How nice. 1 second. So it's 2's divide out, and we're left with a nice negative 3 plus 1. Okay, the 2 divided by 2 cancel out. If you guys want to see this a different way, I'll write it on the side. Negative 3 over 2 times 2 plus 1. You can multiply the 3 and the 2 first. Becomes negative 6 over 2 plus 1. And this still divides out to become negative 3 plus 1. So whether you want to multiply first or divide, I always recommend dividing if you can. Simplify that fraction. So we're left with negative 3 plus 1 is negative 2. And let's just find negative 2 here, just to say this. At 1, 2, we're at negative 2. So this is the point 2, negative 2. But just like in Algebra 1, we said, and someone just commented, can't we just graph this? And you're 100% correct. We can just graph this. We can just jump to the graph. We can go from our y-intercept, we can walk down a rise of negative 1, negative 2, negative 3. That's a rise of negative 3. And we're going to run positive 2. We can continue that pattern over and over and over again. Down 1, 2, 3, and run 2. And then we can draw our line. Okay. Now let's make a prediction. Let's make a prediction what that next point on the line was going to be. I counted it. Let's make that prediction. From this point here, negative 2, what's our rise? We're going to go down 3. So we're going to minus 3 from this. So we should end up with a negative 5 on my y value. And we're going to run plus 2. So take a look what I did there. Rise over run. We're going to rise negative 3 because we're going to go lower by 3 steps. And we're going to run by positive 2. So that should lead us to 4. So that should be my next answer. I would keep crawling this way, down and down and down. Now, let's see if this makes sense. If I plug in a 4 here, let's just double check it. Now again, I chose nice values that can be divided by this denominator. Whoops, I don't know why I copied that. By this denominator 2. So is 4 divisible by 2? Yeah, make my life easy. Make your life easy. So just easy hints that you might have forgotten. 4 divided by 2, those cancel out to become 3 times 2 plus 1. That's going to be negative 6 plus 1 is the negative 5 we were hoping for. All the stars have aligned. And that's exactly what we were hoping for. Now, and that's the idea of there's more than one way of getting to the same answer. Graphing is actually one of the easiest, turns out, than me cranking out every problem by myself. Let's do it one more fancy way. One more fancy way. Here we go. Show you guys one more fancy way. If we know our start value is 0, start here, start here. Please know my start value. Remember, we said my run is plus 2, my rise is minus 3. Wait, well, minus rise over run, negative 3, right? Okay, so here we go. What is 0 plus 2? Isn't that 2? We're there. What is 1 minus 3? Negative 2. We're there. What is 2 plus 2? Becomes 4. Remember, this is my run, x change. And what is my y change? Negative 2 minus 3 is negative 5. So we could build out this chart without actually plugging in that equation. Right? Okay. So let's see. Some other characteristics about this are, what else can we say? Let's talk about graphing real quick. So y is equal to a negative 5 over 4 plus x plus 3. So when you're graphing lines, you need two characteristics because you need 2 points. A line consists of 2 points. If you don't give me 2 points, you can't draw a line. If you just have 1 point, where are you going to go? Which way are you going to go? What are you going to do? So to find those 2 points, we're going to look at these characteristics again. We have the slope and the y-intercept. So we always start off, when we're graphing lines, start off with a constant. Why is it a constant? Because when x is 0, we're going to be left with the y value 3. 1, 2, 3. Not changing. Easiest point you can ever come up with. And one of the things you probably learned in Algebra 1, plug in 0. 0 is an easy number to plug in. Now, from this first point, we still have to find a second point. And the cool thing is because we know about the characteristics about this equation, not just plugging in, not just memorizing it, but we know that there's characteristics that x is changing. How is x changing? X is changing at a rate of negative 5 over 4. So from this point, we can crawl down and follow the steps, negative 1, 2, 3, 4, 5, and run 1, 2, 3, 4. Now, a couple things you want to include to this line to make this look a little nicer. First is that you want to draw little arrows to remind yourself that this line doesn't stop here. It goes on forever. I'm just too lazy to draw the rest. Just too lazy. That's just what it is. But these arrows help you show everyone in the world that they don't stop here. The next thing is, if I told you this point is, if x is 0, we said y was 3. You can come up with the next point just by doing what we did in the last problem. My rise was 4. Sorry, my rise was negative 5. So 3 minus 5 becomes negative 2, right? $3 minus $5, I owe $2 still. My run, we declared my rise and my run. We declared that was 4. So to get from 0, 4 spaces over, 0 plus 4 is 4. You could count. Some people like counting. They like counting. This is negative 1, negative 2, 1, 2, 3, 4. Hey, you can do that also, right? Negative 1, negative 2, 1, 2, 3, 4. Do that also. This is 4, negative 2. So graphing lines are fairly simple. A couple of things that you want to be aware of is graphing horizontal versus vertical lines. So vertical lines are up and down. Horizontal lines are left and right. So for horizontal lines, let me ask you, I'm going to draw this example here, and you tell me, would that be an x value or a y value? Just as a reminder. So look at the red line here. What is changing and what is not changing? X is 1, y is 3. X is 2, y is 3. X is 3, y is 3. So what's not changing? Isn't y not changing? Thank you. Y is not changing, right? It's 3. So for a vertical line, let's draw this again. Just reiterate. So vertical line 1, 2, 3. So we see x is 3, and y could be changing. Now, we have a constant here, but what is stuck? We have x is stuck at 3 now. I don't care what y is. I don't care what y is. As long as x is 3, we're good. So whenever, it's almost counterintuitive, where we think y should be up and down, y is actually horizontal because you're stuck. Imagine if you're stuck on the 3rd floor. You're stuck there. Okay? We're stuck here on x. X is 3. I don't care about what happens to y. I'm stuck on x is 3. Okay, so that's just a reminder so you don't graph the wrong way. Oftentimes we think x is horizontal. You're right, that's a horizontal on my x-axis. But when I'm graphing x is 3, I don't care what y is. It could be 1, 2, 3. It could be all these points here. That gives me that vertical line. While when I'm graphing a horizontal line, that's a y value. Okay. Okay, let's do one more thing here. And we're going to talk about how to get slope-intercept form if it's not given. And this is about simplifying. So let's give you a problem. Simple graph y is equal to 3x plus 2. We know how to graph that. We just kind of talked about it just now. But what if I gave you this instead? What if I gave you y is equal to x plus 2 plus 2x? First thing I want to make note is this is still a line graph. Because do we see x squared? Do we see an absolute value of x? We just see x. Because it's an x graph, not x squared or anything funny, this is still a line graph. So my goal is to get y equals to mx plus b. If I could get into this form, this would be the easiest graph in the world. And some of you guys probably are thinking, Mr. Ko, combine the x's. And you're right, thank you. Now, a simple mistake that people are gonna do, they're gonna subtract -2 to both sides. But they're already on the same side. So please don't fall into this trap. And this is a trap that happens to Algebra 1 kids a lot. You don't want to subtract from the same side. You're not balancing out the equation. What happens is, since they're already on the same side, that just combine it. And if you learn your terms for associated property and commutative property, we can add and subtract in different orders. In this case, we can add our x's together. So x plus 2x plus 2, rewriting the order. So it's 3x plus 2, which gives us the exact same graph that we had before. Another thing that we could do, so this is my first example of something kind of weird. What if I give you another problem that's kind of weird? What if I wrote y plus 2x is equal to 5x plus 2? Is this still a line graph? Do we see only x here? Yeah, this is still a line graph. So our goal again is to get back to y is equal to mx plus b. And in Algebra 1, you get y alone. Y just wants to be alone. Just leave him alone, man. He's having a tough day. So to get y alone, we want to get rid of the x on the wrong side here. Right? He's making us sad. So here's where we use the opposite operations. The opposite of plus 2 is minus 2x to both sides. I'm going to write it right next to the 5x. Some of us might forget, and you're probably not going to do this, but you're not going to write it like over here, right? Those aren't like terms. And that brings us another review of talking about like terms. Like terms are stuff like x's here, where we can relate them together and we can combine them. Y is equal to 3x plus 2. Back to our easy graph. Now let's do one more super messy one. Y minus, oh sorry, plus, let's do 4 is equal to 3x plus 2. Okay. I have a parentheses, I have numbers on both sides. This doesn't look like a line equation right away. But again, going back to the characteristics, is this x squared? Am I ever going to get x squared here? Do you guys see absolute value signs? Nope. So this is going to go back to a line equation. So our goal again, y equals to mx plus b. Get y alone. Get y alone. Just leave him alone. Now the first goal I would do here is to simplify the problem, and I would distribute the parentheses. So 3 multiplies the x as well as the 2. Y plus 4 is equal to 3x plus 6. Subtract the 4 to both sides. Y is equal to 3x plus 2. Back to an easy state. Okay, that's an easy version of this problem. I'll make it one step harder with fractions. So this one won't be pretty. This will just be y plus 4 is equal to 3 over 2 times 4x plus 6. Okay. Now, this is just to help us review fractions when I multiply fractions out. Similar to our last problem, except now with a 3 over 2. So we're going to distribute the front, distribute to the back. I'm going to write this on the side so you can see it. 3 over 2 times 4, and 3 over 2 times 6. Okay, for the first 3 over 2 times 4, the 4 and the 2 divide out, leaving me just a 2. That becomes a nice, easy 6. Whoops, easy 6. In the back, 6 and 3 divide out. 6 and 2 divide out, gosh. 6 and 2 divide out, leaving me a 3. 3 times 3 is 9. Rewriting the problem, y plus 4 is equal to 2 over, whoop, darn it, what am I doing? We said that simplified out to be 6x plus 9. We minus 4 to both sides to simplify the problem. Okay, let's graph this just so we can do it. My m is 6, so it's 6 over 1, as we talked about in Algebra 1. You can write the invisible 1. And my y-intercept, b, is negative 5. Graph doesn't have to be 100% perfect, but it has to illustrate what's going on. It's negative 5, put a dot. Okay, that's my y-intercept. That's where it crashes into the y-axis.
Mr. Kyle, I think the 5s are positive.
Oops.
Yeah, the 5
Oh, thank you. Sorry. You're right. Darn it. 1, 2, 3, 4, 5. Up here. Thanks for catching that. The y-intercept. And then our slope is going to be 6 over 1. Now, we could count 1, 2, 3, 4, 5, 6 going up here. But remember, from Algebra 1, instead of writing 6 over 1, we can write instead negative 6 over negative 1. We can throw negatives in there and go backwards. 1, whoops, change color. 1, 2, 3, 4, 5, 6, and then back 1. One cool thing, we can try this. If we know the point is 0, 5, and we know the slope is 6 over 1, or negative 6 over negative 1, we can subtract. What is 5 minus 6? That takes us to -1. And 0 minus 1 is -1. Hey, that's the exact point we're looking for. Right? We can just subtract it from any initial point that we know. So, great question of why did I do this? Okay, it's because I didn't want a graph up here, because then I would have to extend my graph. So instead of graphing forward to the next point, we can go back to our last point. And one thing about slope, if you remember, you can always make them negative, because what's a -6 divided by -1? It still gives us our +6/1. You can do this the same with fractions that are negative. If I write -3/2 is the same as -3 divided by +2. Or this could be 3/2, as long as you only have one negative. For regular numbers, if I say 5/7, can be written as -5/7. These are both equivalent statements, and it's one of the tools that we learn that we can just add it in there in case I don't want to go off the graph. It saves me time. It saves me work.